Okay, thank you very much. So thank you to the organizers for the possibility to be here and for scheduling the talk at 2 p.m. It's about 8 a.m. In New York, so hopefully I'll wake up soon. So this talk is on inverse problems, often referred to as hybrid inverse problems or coupled physics inverse problems. And their main reason for being there is that we try to combine high contrast and high resolution, which is what most inverse problems try to achieve. So let me give you a little bit of background for what these problems are, and then I'll go more into some details on some results, mathematical results that we obtain on these problems with a list of collaborators that you see here. All right, so in an inverse problem, and I mostly think for applications in medical imaging, what we're first interested in is finding some contrast between diseased tissues and healthy tissues. And we've heard about the Calderon problem. The electrical conductivity of tissues is a good such parameter with a high contrast. And so we inject currents into tissues. We see where the electrons come back. And from this, we try to infer the conductivity of the tissues inside. This is the problem that we heard about this morning. And as electrons propagate to the tissues, they scatter a lot. And by the time they make it outside of the domain, you don't really know where they come from. And that physical phenomenon creates some difficulties in the resolution of the inverse problem. This translates mathematically into those logarithmic stability estimates that we saw this morning. And in spite of a lot of effort, this method is inherently low resolution. Depends how you mean what you mean by resolution, but typically people are interested in, let's say, sub-millimeter resolution, and that's something that's relatively difficult to achieve with the IT, even though there are some great methods, numerical methods out there to solve this problem. All right, so we have a method with high contrast, relatively low resolution. There are some other modalities that have high resolution and also sometimes high contrast, but in some cases low contrast. So I will talk a little bit about ultrasound. So we're familiar with this type of pictures where we can see relatively clearly there's a high contrast between where there are bones and where there are tissues. However, tissues for sound are mostly bags of water, and whether they're healthy or not, you don't really see the difference between healthy and diseased tissues. And so for the purpose of reconstructing tissue properties, this method is low contrast. So we have the resolution, sub-millimeter resolution that we're interested in, but we've lost the contrast. Okay, so are there some modalities, methodologies that allow us to get both the high contrast and the high resolution? Well, one way to try and achieve this is to combine one method with high contrast, low resolution, one method with high resolution, low contrast. And then it turns out that in many cases, physics comes to the rescue and introduces a coupling, or does a coupling. There's a physical coupling between a modality of the first category, high contrast, low resolution, and a modality of the second category, high resolution, low contrast. And so those are the inverse problems that I will talk about. So again, they're often referred to as hybrid inverse problems. They have good properties of stability, as you will see. However, they're a relatively low signal because this physical coupling is typically relatively weak. All right, so let me give you a set of examples of such coupled physics inverse problems, and then I'll dive into their mathematical analysis. So the first one combines optical properties, which are very similar to electrical properties when you send photons into tissues. I don't know if you can see the red glow. The photons do propagate in tissues. By the time they make it outside of the domain, they're also, they've scattered a lot, and so they're extremely diffuse. And so there's a good contrast in the optical properties, but we get them with relatively low resolution. So the photo part is the high resolution, high contrast, low resolution modality, and the ultrasound, the acoustic part, provides the resolution. Okay, so I'll come back to this modality in more detail, but there's here a coupling between optics and ultrasound. There's been, and here's a typical picture that you can get. This is in Paul Beard's lab at UCL. You see relatively good contrast between blood and no blood, because blood absorbs differently than the surrounding tissues, and you see the vasculature with high resolution, something that you cannot do with purely optical techniques. All right, so there are other modalities of a similar flavor. Elastography is one of them. It combines elastic waves. You have elastic waves propagating shear waves, mostly propagating through tissues, and they are coupled with either MRI here or ultrasound. So elastic waves are combined with MRI and ultrasound. These are two other modalities that seem to be working quite well. Polyman, Dick Eman is using those techniques at Mayo Clinic relatively efficiently to get an idea of how disease the liver might be. All right, so those are two other couplings. Here's another one that we'll also mention, which is another coupling of optics with ultrasound, which is called ultrasound modulation. So there are various ways of coupling a modality with high resolution and low contrast, and a modality with low resolution, high contrast. And these methods have been introduced mostly by bioengineers, by physicists, and there's a very highly growing literature on this type of problems. And you can also see from the mathematical literature that several people, including some who will speak here, Habib might talk about this here later this week, and Fauzi will talk about similar problems later today. All right, and so I've been involved with looking at these problems for the past 5-6 years. And in the modalities that I've presented, the first one with a mouse is referred to as Photo-Acoustic Tomography. It's one of these acronyms here. Several of the other modalities are also shown here. And so I will talk about several papers that try to solve one modality or understand mathematically what happens in one modality, and then I'll move to another modality, show you what happens in that new modality. What I'd like to talk about is an attempt to provide some theories that somehow apply, don't give necessarily the most precise results, but apply to a lot of those modalities so that we can understand, before we do experiments, why the method might or might not work and what it is we can reconstruct. Okay, so let me come back to the photoacoustic effect and go to the mathematics of it. So before I do this, let me briefly mention the mechanism. Where is that coupling coming from? Turns out that as we send photons through tissues, femtosecond pulses, it has to be done in the time domain, although you won't see it here. You send femtosecond radiation pulses that propagate through the tissues. Think of it as photons. As the photons propagate, some of them get absorbed. When the photons are absorbed, they heat up the medium a little bit. When the medium heats up, it expands. And when the medium expands, it emits some ultrasonic waves, ultrasound, okay, like when we speak. We have ultrasonic, and this ultrasound signal is very, very small. But today's equipment allows us to still measure that signal. And so we have an ultrasound measurement trying to help us reconstruct optical properties of the tissue. So we can get the high contrast of the optical properties with, hopefully, the high resolution of the ultrasound. Okay, so that's how this technique works. All right, so mathematically, we have to model both phenomena. Obviously, we'll assume that we have a diffusive regime for how photons propagate. U here is the density of photons. F is how you send the photons, and you can send photons from one direction, from another direction. So there are various ways of acquiring information. This F here, the index J, refers to the number of experiments that you're doing. Photons propagate through the tissue. The density is given by this uj, and the parameters that are not known are the optical parameters. There's two of them, at least in a scalar version of this equation. One is the absorption coefficient, and the other one is the diffusion coefficient that we saw quite a few times this morning. All right, so those are two unknown parameters. U is also not known a priori, obviously. It's the solution of the equation. And as photons propagate, as I said, they get absorbed. So sigma times U depends on how many photons made it there, and sigma is the rate of absorption. Sigma times U is a quantity of photons that are being absorbed. And then, as I mentioned, the photons that are absorbed heat up the medium, expand the medium, and then some signal is propagating. That's all lumped into that Green-Eisen so-called coefficient, big gamma here, which tells us how much acoustic signal is propagated. We send pulses of light. As far as sound is concerned, everything happens at time 0 because the ultrasonic waves propagate much more slowly than electromagnetic waves. So this absorption occurs at time 0 as far as the wave is concerned. There's a signal that is emitted at time 0. That signal solves a wave equation, propagates according to the laws of that scalar wave equation here to simplify. And we have ultrasonic detectors at the boundary of the domain. So for X at the boundary of the domain, assuming that we have detectors surrounding the domain of interest, which is the idealization that I'm going to assume here, as a function of time, you get all this information. Okay, so the unknown coefficients, there's 3 of them. The diffusion coefficient, assuming again that it's scalar, and then later I'll assume that it's matrix valued, tensor valued. Gamma is the unknown diffusion coefficient, sigma is the unknown absorption coefficient, and big gamma is also an unknown Green-Eisen coefficient. That's what we want to reconstruct from what? From the data, the ultrasonic data that we have acquired.
So is it possible that one place is designed to optimize the acoustic excitation?
Yes, in this model, all I'm assuming is that the pulse is sufficiently short so that everything occurs at time 0. Otherwise, we're losing resolution. And I don't think that the frequency of the pulse has much of an influence. So both punch lengths and this, it's relatively broadband, my understanding, in what they do in practice. And the pulse length has to be in the femtosecond regime so that you have a good separation, a time scale separations between the light and absorption and ultrasound behaviors. Okay, so that's actually a relatively big assumption, which is not always true. When the pulses become long in time, and there are some applications in which the pulses are long in time, this approximation that everything occurs at time 0 is not very accurate, and then we lose the resolution. So where is the resolution coming from? Here is now happening here. I will assume that everything is relatively simple at the level of the ultrasound. The ultrasound that we have measured, we will assume that the signal has propagated in a medium that we know, and let's simplify, in a medium that has a sound speed which is constant, which is not completely, not a bad hypothesis for a mouse. A mouse can, to a first approximation, be replaced by a bag of water. It's not that inaccurate. Okay, so let's assume that the sound speed is just that of water, and let's assume that sound just propagating according to that law. Now, if you measure a wave signal at the boundary of the domain, wave equation is time reversible. All you have to do is to take your signal, time reverse it, sending back into the medium by standard time reversal, say. And the signal will back propagate to where it came from. So here is time reversal explicited. The information that we have acquired, we do something to it, and we get, which is time reversal, and back propagation according to the laws of that wave equation. What we get is our initial condition back. So there's an explicit expression when the sound speed is constant and known that gives us this quantity here, which I will always refer to as H. It's the initial condition for the acoustic pressure. That's not quite what we want. What we want is those coefficients, lil gamma, lil sigma, and big gamma. What we have reconstructed is the initial condition, which is that product here, big gamma times lil sigma times uj. Okay, so the new type of inverse problem, quote unquote, is an inverse problem where you have the constraints we're familiar with. These are the PD constraints. And there's a new constraint that comes from us solving a first problem, which we assume is done well, and there can be some difficulties with this. But I will assume for the rest of the talk that the first part has been solved. The high resolution modality has been solved one way or another. And what comes out of this solution is an internal functional of the parameters we're interested in, big gamma and little sigma, and also a functional of the solution of the PDE that we also don't know. Okay, so all the hybrid inverse problems are of this kind. We have unknown parameters. We have PDEs constraining whatever probing mechanism you're using, and you have this new constraint which, instead of being a boundary measurement, now has become an internal measurement. It's defined for every point x inside the domain. Because we have solved the problem. We didn't put detectors inside the domain. We have solved the first boundary inverse problem, which we assume is well posed and high resolution. Okay, so if everything is okay, we have a new functional which now, there's no, the resolution is already, the high resolution comes from us acquiring that functional carefully by solving applying that formula, if you wish, assuming that is valid, solving that first high resolution inverse problem. Okay, so now what's interesting about this problem is that we can make as many experiments as we wish or as the patient allows. It's always obviously time consuming and to make new experiments, but as I mentioned earlier, this F is an information about how you send photons into the tissues, and you can repeat the experiments with various ways of sending photons into the tissues. And the question is, how many experiments should we do? What can we reconstruct as a function of the number of experiments we're doing? How is stability affected with the number of experiments we're doing? Okay, the math will answer those questions. What is it among those coefficients that we can reconstruct depending on the number of measurements we're making? And is the number of measurements we're making changing the stability with which we are gaining those coefficients? And okay, the answer will be yes to make it interesting. All right, so how about that specific problem of quantitative pad before I move to other problems? Again, I repeat that you can forget about essentially everything I've mentioned so far. We now have a PDE for uj with unknown coefficients gamma and sigma, and obviously u is also unknown because it's the solution of this equation. And we have a new constraint, which is that linear constraint here in both sigma and u, bilinear trilinear actually in all the coefficients here. We have these new constraints that we want to use for the reconstruction. So here's the full theory for that problem. There's something that's somewhat negative, but here's the result. Let's assume that we send photons through the tissues in two different ways. The F1 and F2 are not proportional to one another. So linearly independent F1 and F2. We have two H's that come to internal functionals that come from these experiments. Let's construct this vector field beta, which is essentially the gradient of H2 over H1, or similarly the gradient of U2 over U1. Let's assume that that vector field is not 0 and sufficiently smooth, which is a difficulty. Then here's the result. Once we have those measurements, what we can reconstruct is those two quantities, chi and q, and that's it. We cannot reconstruct anything else from those two measurements. But what is worse is that any additional measurement that you might make is already a functional of those two first measurements that are made. So I send photons this way, first way, second way. There's no point in sending photons a third way. A priori, that new measurement that you would make is a functional. I can construct it directly from those two coefficients, H1 and H2. So a priori, there's no need for a third experiment, at least as far as injectivity and uniqueness is concerned. That's a bad result because we have three coefficients to reconstruct, and we have essentially two independent, not linearly, but we have two independent functionals, and that's all we get. So those two independent functionals allow us to reconstruct those quantities. Here you might recognize the Liouville transform, how we go from the Calderon problem to the reconstruction of a potential. This is the same type of algebra that shows up here. And there's a new coefficient that shows up here. That's all we can get out of the three coefficients. Those are the two coefficients we can get. So it's a negative result. In some way, independent of the number of measurements that you're making, you cannot reconstruct everything. Those are only the two coefficients you can reconstruct. In practice, we can assume that the Green-Eisen coefficient is known, And then you can look at those coefficients carefully, and you observe that this is a nonlinear problem, but it's a relatively classical one. You can prove that. Then the optical coefficients can be reconstructed. Okay, so that's one first result. Now, how about stability? I don't want to delve too much into the details of how you do this, but that's something that's not very difficult. Maybe you can we can see it from here. There's an equation for U1. Let's multiply it by U2. The equation for U2, let's multiply it by U1. Subtract. Sigma U1, U2 is gone. And you have an equation that involves U2 grad U1 and U1 grad U2, and you can write it as a gradient of U2 over U1. You are very close from the reconstruction. That's how the formula goes. There's an explicit formulation for K and Q, essentially for your nose, and you see that tweaking those equations a little bit gives us K and Q relatively quickly. Okay, so this explicit formulation allows us then to look at the stability estimate. If we have two measurements, H1, H2, and H tilde 1, H tilde 2, and we assume that we've made some errors between H and H tilde, how is this error propagating into the reconstruction? What is the stability estimate of that problem? Well, what we can obtain is that, assuming that that vector field is bounded from below by a constant, so that's a big if, we have, remember that beta is the gradient of the ratio of two solutions. We want that gradient to be bounded away from 0, which means that you have to choose the f's carefully so that this is the case. I will come back to that problem later a little bit. So let's assume that our vector field beta is bounded away from 0. Then we can prove that there's an optimal stability estimate, which is that we lose two derivatives in the reconstruction of gamma and sigma. That's a positive result. We lose two derivatives. We don't lose an infinite number of derivatives, as is the case for the Calderon problem. So it's much better posed than the Calderon problem. We don't have a logarithmic estimate. We really have a bona fide Lipschitz estimate, provided that we lose two derivatives. Okay, so Lipschitz or Hölder type estimates. That's what we can get. It's much better than the Calderon problem, but we've lost two derivatives nonetheless. Can we improve that estimate? Well, it turns out that by making more measurements, we can render the problem more stable. I mentioned to you that acquiring a measurement H3 was not useful for uniqueness. H1 and H2 uniquely characterize H3. But you have to do some work to get H3 out of H1 and H2, and you have to differentiate multiple times to get H3 out of H1 and H2. So if H3 is given to you, you don't need to differentiate anymore. And here's the results that tells us that if you have not 2, but n plus 1 measurements where n is dimension, and that's also something that's optimal. We need n plus 1 measurements. Then we can reconstruct the same gamma and sigma. This is now an overdetermined problem. We have more information than necessary. We still reconstruct 2 coefficients, but we have, say, 4 data in 3 dimensions. Then you see that we don't lose any derivative in sigma anymore, and we lose 1 derivative in gamma. So it's much better stability estimates. And those estimates are now optimal. Okay, so I'll show you a similar example in another problem, and I'll try to derive some, why is that the case? Why do we improve stability going from this setting to that setting? Are there some global principles that we can try to follow? Okay, so that will be what I want to show in the talk. Numerically, we also observe similar properties. If this is what you want to reconstruct, maybe the contrast between blue and red is not that great on the screen here. It's much better on my end. If you do reconstructions in the absence of noise following that procedure, which I didn't show you, you get perfect reconstructions. Now, if you add some noise, I don't remember how much, this is what you get. These are reconstructions that you get. Remember that we have to differentiate the data, so we have to regularize them, sweep under the rug, all the standard regularization techniques that you use when you lose derivatives. But after regularization, relatively careful regularization, this is what we get. These are the reconstructions we get. You see they are blurry. Now, if instead of 2 measurements, we make more measurements, here 10, we don't need 10, but this was the number that we had in that experiment, you see that the reconstructions are significantly better. So this is not a proof of the theoretical estimates, but at least it's consistent with the theoretical estimates. By acquiring more data, you significantly improve the reconstructions. Okay, so it's useful to ask the patient to stay another 10 minutes, potentially, in the machine to get higher resolution reconstructions. All right, so why is that? let me first backtrack and mention that all these hybrid inverse problems, many hybrid inverse problems, have a similar flavor. So the one I've talked about is the one where we try to reconstruct the optical parameters from this type of internal information, not internal functional. There's a whole zoology of hybrid inverse primes, coupled physics inverse primes, where you can take any high resolution and any high contrast methodology and hope that physics provides a coupling, which it does or it does not. But several of them are actually relatively useful. Some of them are potentially useful, but the signals are so weak that we can't really use them in practice. Ultrasound modulation, unfortunately, is one of them. But okay, let's assume that we can solve that high resolution problem, and that we have extracted new functionals, internal functionals from that first step. Then the problems look like this. You have a PDE, and you have a new constraint, internal constraint. And depending on the modality of interest, photoacoustics, elastography, ultrasound modulation, MREIT is coupling of elastography with magnetic resonance imaging. Depending on the modality, you have different internal information. And so again, to repeat what I said earlier, we can choose how we send photons or something else into the tissues, photons or electromagnetic waves. Doesn't need to be scalar, doesn't need to be a diffusion equation, it could be Maxwell or elasticity for the principal applications that we have in mind. So we have PD constraints, and we have these new constraints, which you see are polynomials in the coefficients and the solutions of the PD and the derivative of the solution of the PD. So how do we choose the illuminations? How many illuminations do we choose? How is stability related to this choice? That's what I want to talk about now. So I'll still give you another example to present the theory, which is that of ultrasound modulation, where there's only one parameter of interest, gamma. There's no sigma anymore, no big gamma. There's only one parameter that we don't know, gamma. But the functionals are much more complicated than the ones I've mentioned earlier. They are of the form, we know now gamma times grad u squared. And we, let's say, make two experiments. So we have two constraints for the PDs, and we have two additional constraints that come from resolving the high resolution step of the hybrid inverse prime. So let's assume that we have those constraints. We can put to the left what we don't know, put to the right what we know, and what we observe is that for all these problems that I've mentioned so far, it's advantageous to look at it. It's not the only way to look at it, but it's advantageous to look at it as the left-hand side being a polynomial in what we don't know and the derivatives of what we don't know, aka a nonlinear PD. Okay, so we have now gamma and U1 and U2, which we put on the same footing, and we assume that we have a nonlinear PD for U1 and U2. Now, the number of constraints we have depends on the number of experiments we're making. So we are here in the amusing situation that the PD itself changes as a function of the number of experiments you're making. Okay, and this is the analysis of that PD as a function of the number of constraints that makes it, well, somewhat interesting, certainly amusing. All right, so as I mentioned, the inverse problem now is a nonlinear PD. We have those coefficients, gamma, which I still refer to as gamma, and the coefficients uj, which are really on the same footing for the nonlinear PDs. They are all the unknown functions, and we have a polynomial of those objects, which is known. Again, for the ultrasound modulation, this is this specific instance of f. All right, so we are interested in uniqueness, stability, reconstruction procedure, all the standard questions that we're asking ourselves for inverse problems. Okay, so here are some theoretical results. Let me first start with one measurement. After all, as I mentioned, there's only one coefficient we don't know, which is gamma. If we also assume that u is not known, one constraint, one additional constraint for gamma and u gives us two PDs for two constraints. That should be enough. Not only that, but the elimination of gamma is actually relatively straightforward here, so let's do so. And we end up with one PD for one unknown, one scalar unknown. And that's also something that we hopefully can solve. The problem is that that nonlinear PD is of relatively nasty type, even though that constraint is relatively harmless, and the equation that we start with is elliptic. Turns out that the equation that we get this way is not elliptic, and is, as it turns out, strictly hyperbolic, in provided that this direction can be defined. So provided that gradient u does not vanish, then we can prove that this equation is a hyperbolic equation. So I will briefly go through the theory of that equation, but the main result is that we can reconstruct gamma uniquely on a part of the domain, and we are losing one derivative during the reconstruction. So this is just the analysis of a standard a hyperbolic equation. Whenever we have a source term and we solve for a wave equation with a source term, we gain only one derivative and not two when we solve a wave equation, because the wave equation is not elliptic. So we still gain one derivative, but you lose one derivative from the source to the reconstruction. The source would be a delta H here. So we lose one derivative in the reconstruction. And not only that, but we can only reconstruct it on part of the domain. This is a hyperbolic equation. So here's a picture. This is the part of the domain where we can do a good reconstruction. Turns out that we have a wave equation with boundary condition all around the domain. So it's a wave equation in x1, x2, x3, and we have boundary conditions at the boundary of the, let's say, this ball. It turns out that a part of the boundary is time-like, a part of the boundary is space-like. The part of the boundary that's time-like, that looks like t0, we can propagate the information. Now, if you have a wave equation, and you have in dimension 3, in t, x, and y, and you have information that x is equal to 0, you cannot propagate that information stably. And when the coefficients are not constant, not the Laplacian, you have varying coefficients, which are not analytic. We don't even know how to do that construction. So the results as they stand is that this problem can be solved on only a part of the domain, which corresponds to, again, a part of the boundary where information is allowed to propagate. And we lose one derivative in the reconstruction. Okay, so that's the result when we have only one measurement, which is equivalent to the result for two measurements that I mentioned at the beginning for photoacoustics. How about going to a larger number of measurements? So this is where there's a theory that applies to that example that has been applied to several other problems, and hopefully can be applied to all those hybrid inverse problems in relative generality. And this is the following. So we really look at the redundant system now, rather than just the system, the original system with only one measurement. Let's go back to two or more measurements. And the question we're asking ourselves is, if we increase the number of measurements at some point, does this problem become elliptic, which corresponds to the optimal stability estimates we can hope for? There's no better than an elliptic stability estimate. That's the best you can hope for. You have, if that operator is elliptic, then V is in an appropriate norm is the same as S in another appropriate norm. You have both sides estimates, and you cannot improve upon such estimates. Okay, which is not the case again for that stability estimate, which comes from solving a hyperbolic equation. It's not optimal. So can we prove that that problem is elliptic? All right. So the standard method for such problems is first to linearize them. We don't have explicit expressions in general for the system, the nonlinear system, so we linearize them, and we look at the operator, the linearized operator. We separate into its principal part and its lower part. Principal in the sense, Agmon-Douglas-Nirenberg sense, which has to be looked at carefully because this is a system, but this is nonetheless the first step that you have to follow. So let me go through that, what this type of theory gives us. The symbol is relatively complicated, but it turns out that geometrically, you remember that each measurement corresponds to a hyperbolic equation. Each measurement gives us a new hyperbolic equation. Now, if we look at the concatenation of several hyperbolic equations, it might become elliptic. So think of a solution U, which is only one u, but it solves several hyperbolic equations for some reason. So u might solve dtt minus Laplace in xy, you know it, and might solve another equation which might be dxx minus Laplace in ty, and also dyy minus Laplace in tx. Let's assume we know all of this. Is that problem elliptic now? And the answer is yes. The problem is elliptic. You can just sum and subtract, and you will see that you will get the full Laplacian of u from that crude example that I've mentioned to you. So geometrically, it turns out that if you look at all the measurements that you've required, each measurement has a light cone associated to it. You look at the intersection of those light cones, that's the geometric property. If the intersection of the light cones is 0, well, which is always in all the light cones, then you're elliptic. If the intersection of the light cone still has some lines that are present, then your problem is not elliptic yet. You have to add measurements. Okay, so we can prove that indeed, if we have n+1 solutions, again it's the same as before, we can prove that n+1 properly chosen solutions have a light cone that intersects 0. And how do we make sure that the solutions how do we choose the boundary conditions for solutions, for such solutions? Well, we choose them by CGO solutions. So again, we need sufficiently explicit expressions for our solutions so that we can verify that the intersection of light cones is the singleton 0. And that's not easy to verify in general. But we can construct solutions which are typically based on CGOs because these are the only solutions that we know that are sufficiently explicit, like for the Calderon problem. We use them, and then we can prove that indeed that geometric constraint is satisfied for properly chosen boundary conditions. Oh, I may come back to that, the choice of boundary conditions later. All right, so let's assume that we have chosen boundary conditions such that the intersection of these light cones is indeed 0. Then we're in good shape. We have ellipticity inside the domain. Again, it's ellipticity in the sense of Douglas-Nierenberg because these are systems. You have to be a little careful on how you define ellipticity, but it's true, and these are standard, not very well-known theory, but standard theories nonetheless. Once you have ellipticity inside the domain, you need to make sure that you find boundary conditions that are compatible with this ellipticity, that have to satisfy the Lopatinsky condition. You verify that on the specific example of interest, you can choose boundary conditions such that this is the case. And once you've done this, you are in the setting of application of the Agmon-Douglas-Nierenberg theory, which has been extended by Solonikov in the early 70s to overdetermined systems, which tells you the following. You have a linear system to solve. It turns out that linear system admits a left parametrics. So it's not an invertibility yet, but at least you have completely inverted the high frequencies. Once you have applied your left parametrics, it's a microlocal result. Once you have applied the left parametrics, you have identity plus something which is smoothing. And you can make it as smoothing as you want, provided that the solution, that the coefficients are sufficiently smooth. Okay, so that's the result we get. Practically, why did we do this? Well, associated to that parametrics, we have a good understanding of what the parametrics looks like by potential theories. We have an understanding of how singularities propagate through they don't move, but how singularities, how high frequencies are reconstructed in that problem. And so for the problem of ultrasound modulation, if we look at the stability estimates associated with this Agmon-Douglas-Nierenberg theory, we obtain that the solution, delta gamma, is of the same order as delta H. We no longer need to differentiate anymore. This loss of one derivative that we had observed for the hyperbolic problem is now gone. We have a bona fide elliptic estimate, which for that specific problem tells us that we can reconstruct delta gamma with no loss of derivatives. Okay, but we don't have injectivity yet. The parametrics gives us the presence of a compact operator, and 1 could very well be an eigenvalue of that compact operator, and hence the presence of a delta u's here. So delta u, which is not known, appears here. So we cannot obtain injectivity from such a result, nor should we expect it. Think of Laplace plus potential. There are some potentials, so that Laplace plus potential is not invertible. It's the same thing here. So if you really insist on having injectivity, then we follow standard routes, but it's relatively difficult to put in place. So one of them is to follow some Holmgren theory, assuming that the coefficients are analytic or close to analytic. Then we can obtain an injectivity result, or we can see whether we can obtain some unique continuation result, which for me here was done by looking at Calderon's result of unique continuation as it was revisited by Nirenberg, and see how we could apply that theory to that setting here of redundant systems. So what they had done was for symmetric systems, and okay, the results were not quite what I needed. So I believe I have a slide here. For specific problems, this is unfortunately the only uniqueness result that I know, and this is a lot of work for something which practically is not necessarily the most interesting. I think the stability estimates are the most interesting from the practical point of view. But nonetheless, it turns out that for the ultrasound modulated problem, we can rewrite it as a system where P1 just satisfies a standard UCP, and P2 is elliptic with simple complex roots. There are some difficulties that David mentioned this morning, that not every linear problem satisfies, even scalar, satisfies a unique continuation principle. There are the Levy counterexamples that create some difficulties. So you have to make sure that you are not in the framework where the Levy counterexamples can apply. And so, all right, so you have to look at the roots of those operators. Let me not mention that further. You can look at that. This was coming from, this is now published. I think this is the same as here. This is now published in the Irvine Günther Ullmann book. All right, so let's assume that we have now solved the linear problem. We have both the good stability properties that we wanted. We also have an injectivity. Once we have those properties, we can go back to the nonlinear problem and use some Newton-type result to prove that once we have uniqueness of the linearized problem, at least locally, we expect to have uniqueness of the nonlinear problem, and this is indeed the case. All right, so a lot of work for getting those results. Let me try to show you some reasons why those ellipticity estimates might be useful. This is here a reconstruction with two measurements. We're in 2 dimensions. 2 measurements in 2 dimensions is enough. This is a reconstruction. This is what we want to reconstruct. This is a reconstruction with only 1 measurement, where we've not really optimized the reconstruction, but this is the setting in which we hope to reconstruct the solution only on part of the domain. And you see that the algorithm that we are using, which is standard algorithm to reconstruct such problems, doesn't really work very well. So we move to 2 measurements. Now it turns out that when you have 2 measurements, there's still a possibility to violate the ellipticity condition. The way the 2 measurements were constructed is the only way to actually violate the ellipticity condition, but it's still an interesting result. We assume that we have a solution which looks like x1. The gradient of x1 is e1. This is, to a first approximation, we put at the boundary of the domain x1. Now, you have a solution whose gradient points in a direction. What's the most orthogonal to this? Let's look at the solution whose gradient is e2. So we look at the solution with x2 being the boundary condition of the domain. Typically, these are the most linearly independent solutions. The problem is that E1 has a light cone which is a cross. So E1 has a light cone which is a cross with lines at 45 degrees, and E2 has a light cone which is the cross at 45 degrees, same cone. So it turns out that the 2 light cones are actually the same. And so even though we have 2 solutions, we are violating the ellipticity condition, and we can actually apply Hermann-Der's propagation of singularity result here. And you see that numerically it's quite remarkable. We see some artifacts that come exactly from propagation of errors that are generated here at the boundary of objects, and you see that these errors propagate through domain by standard propagation of singularities in a hyperbolic problem. So you see that numerically making sure that the solutions satisfy the ellipticity constraint gives us much better reconstruction. Okay, so I'm running out of time soon, so let me mention two aspects of those problems very briefly. For J small, we run into the difficulty that the estimates might not be optimal. For J larger, we have much better and optimal stability estimates, much better results. Is there an interest in going even to larger numbers of solutions? The answer is yes, if you want explicit reconstruction procedure. So that's just what I want to say. It's not necessarily, so here are examples in which this was applied. Okay, let me move to to this result here, where we have functional of this kind. They are slightly different from the ones before. It turns out that if you have a lot of such functionals, the number of information is so overwhelming that you can do local algebraic manipulations that almost solve your system. And so this is relatively complicated to explain here, but for that specific problem, what we obtain by local algebraic manipulations is a reconstruction of the gradient of the solution, not necessarily the solutions we're interested in, but the gradient. So what this buys us, I will not say much more than this, what this buys us to have more functionals, more solutions, is that at some point the information is so redundant that local algebraic manipulations, which are not easy, but local algebraic manipulations gives us explicit reconstructions of the coefficients or something that's close to the coefficient. So that's one point I wanted to make. The other point, the next point I wanted to make was related to anisotropy. So we had the example that David mentioned to us. So I believe I have a slide here that's relatively similar to his. For the Calderon problem, let's assume that we have a coefficient that is now anisotropic, gamma is anisotropic. We know that we cannot reconstruct such a coefficient. We know that we can consider arbitrary changes of variables that preserve the boundary, each point at the boundary, and then we can push forward gamma according to that change of variable. Here's the explicit expression of that push forward. Then it turns out that the boundary measurements are the same for both conductivity. So there's a huge obstruction to reconstruction for the Calderon prime from boundary measurements. Now, for the hybrid inverse primes that I've mentioned, we're using ultrasound to reconstruct functionals inside the domain. This ultrasound comes from us assuming that the sound speed is constant. The sound speed is constant, so it's very easy and not fooled by a change of variables. You know that the sound speed is constant. There's no way you can fool the reconstruction of the internal functionals. So you can reconstruct internal functionals. And once you have internal functionals, you're sitting on top of a point. You cannot be fooled by a change of variables either, because you're really sitting at every point where you want to do reconstruction. So I don't know if what I mentioned convinces you, but the results are that if you have equations, similar equations to what I've mentioned, so let's go back to that one, with an A now, which is an arbitrary diffusion coefficient, diffusion tensor, complex valued. In some cases, it's useful to have complex valued coefficients to account for various dispersive effects. So C could also be a complex valued coefficient. Work that we did with Günther shows that if you have a sufficiently large number of U's itself, we know the solution now, then we can reconstruct complex valued and anisotropic coefficients with similar stability estimates to what I've mentioned. There's an elliptic theory behind all this that you have to go through. But we can do reconstructions for specific problems of interest of anisotropic coefficients. Okay, so that's the last point I wanted to make. And let me show you some numerical simulations of anisotropic coefficients. I don't know really. These are two components of an anisotropic coefficient, and you see that in the absence of noise, we do perfect reconstructions in one of the algorithms that I did not mention. And in the presence of noise, we do, well, reasonable reconstructions, provided that the ellipticity constraints are satisfied. So that's something I want to mention again here. These are reconstructions. This is the object we want to start with. These are reconstructions in the absence of noise. And these are reconstructions in the presence of noise. And you see that in the presence of noise, the reconstruction is very poor. And why is it poor? It's poor because we assume here that we have Dirichlet or Neumann conditions on those three sides. Think of several solutions having linearly independent gradients. It's not quite what we need, but it's close to what we need. We need solutions with linearly independent gradients. The solutions are bound to be zero here. So the gradient along the boundary is fixed and zero. So they are clearly not linearly independent close to the boundary. And sure enough, reconstructions close to the boundary degrade significantly because whatever ellipticity condition, whatever determinant we need to be away from zero is less and less away from zero for certain conditions, and as soon as you add a little bit of noise, your reconstructions degrade. Okay, so this is the type of results that we have obtained that are numerically somewhat consistent with the theory. Here is one last. I want to show you data. So these are data for another prime. This is what you observe. This is internal information, but this doesn't provide the solutions nonetheless. You have to work relatively hard to get to extract anything out of this. And here are the reconstructions. This is the anisotropy. This is the determinant. Here, the ellipticity theory tells us the determinant should be much better reconstructed in the presence of noise than the anisotropy. And this is indeed the case. These are reconstructions in the absence of noise. You see the crab showing up here because numerically there's always a little bit of noise. But as soon as noise increases, we see that the reconstruction of the anisotropy coefficient degrades very quickly, whereas the reconstruction of the determinant does not. And that's, again, consistent with the ellipticity theory, which is here, which says that the reconstruction of the determinant should be better. You don't lose derivatives in the reconstruction of the determinant, whereas you lose one derivative in the reconstruction of the anisotropy. Okay, my time is up, so thank you very much for your attention.